Okay, so this is number 23, chapter 11. It's dealing with an epoxide. And it's NaCN. They're saying it's in ethanol and in water, right? Below the arrow, those are solvents. Right? They want to know what product forms. So, with epoxides, we talked about this today. The epoxides are asymmetrical, meaning there's two carbons that are not the same. Right? This carbon is more substituted. If I number this carbon 1 and that one 2, carbon 2 is more substituted than carbon 1. And we said when we were in basic conditions, we attacked the less substituted. We had negative charges around. If we were in acidic conditions with plus charges, we attacked the more substituted carbon. So what kind of conditions are we in here? Basic. Negatively charged, right? So there's a plus charge in the sodium, but there's also a minus charge in this nitrogen, or carbon, excuse me, the nitrile. So that means we're going to attack which carbon? Carbon 1 or 2? In base, what matters more? Sterics, right? So we're going to attack the less substituted, and that would be, of course, carbon 1. Another tricky thing people mess up here is they won't number their carbons. They'll lose the carbon from the nitrile. So we should have O minus the CN. Right, this is 1, that is 2. The carbons are here. And then, because we're in protic solvent, this oxygen is going to get protonated by one of the solvents. And we're going to end up with the final product, OH, CN, right? The biggest thing people will mess up, they'll lose this carbon along the way or lose this carbon along the way. That's what usually happens. But negative charges, less substituted carbon. Unless you see H plus, like HCl, HI, something like that, H2SO4, it's not acidic conditions. It's going to go into the less substituted carbon. Okay. This one is number 29.
Yeah.
And it's starting with this alkyne. And they're saying from there you're going to make this alkene. And from there you're going to make this carboxylic acid. Alright? So, we should always try to number our carbons, do that kind of stuff. So we'll start at the beginning. Let's just say this is 1 and 2. Where do you think 1 and 2 are at in the second, this other product? Which end are they going to be? Over on this end or over on this end? By the pi bond or not by the pi bond? By the pi bond, I would guess, right? Functional groups kind of, right, they stay there. And where do you think the functional groups will be at in the final thing we're trying to get to? Which carbon's going to be number 2, do you think? Where's it going to be? By the on the carbon of the carboxylic acid? That's what I think. Alright? So you can kind of see, right, where the pi bond was at originally is kind of where the stuff's going to go always in the end. Right? See that? Okay. So we want to work backwards. So how do we make a carboxylic acid? Where does that come from? What's the start material? We know one way to make carboxylic acids. What would that be? No. What do we make carboxylic acids from?
Chromium.
Chromium's a reagent. So what's the start material? That's right. Chromium's right reagent. That's right reagent. What's the start material?
It would be alcohol.
What kind of alcohol? That's right.
A primary.
And work on which carbon?
Carbon 2.
Perfect. Don't lose carbons. 5, 4, 3, 1, 2. Good. For our primary alcohol, what star material could I make a primary alcohol? If I want to make a primary alcohol, this would be like the anti-Markovnikov alcohol. What would that come from? What kind of star material? That's the reagent. BH3 is reagent.
Oh, yeah, I mean.
Yep. So what's the start? What start material would it come from? You're right. Just from an alkene, so it could come from this alkene. And now this alkene could come from what? How do we make alkenes?
H2 palladium and carbon from a triple bond.
Not palladium on carbon, it has to be H2 Lindlars if we want to stop it.
Yes.
If we want to stop it. So that means, Joe's saying, right, it could have came from this triple bond. Number of carbons, 1, 2, 3, 4, 5. Of course, being mindful of the bond angles. Mind the bond angles.
I have a question.
Yep.
Okay, so when I did this initially, I had the triple bond attack the bromine. Or wait, no, the like delta plus side on the carbon attached to the bromine. Is that wrong?
Nope. So what's one step back from here then? Is I would say one step back from here is this. So let's look at the reagents you need to do this. All right. So everybody's okay with this retrosynthetic analysis? So what reagents do we need to go forward here? What's the first thing we need to do?
Attach carbons.
We need to attach carbons, but how am I going to make? How am I going to take that hydrogen off? What reagent do I need to use? NaNH2. That's right. So the first thing you need to use is NaNH2, that strong base. And then what do we add in? How many pieces do we need to add in? How many carbons do we need to add? 3. So we need to add something that has 3 carbons, and then something that's delta plus on the end. So that'd be 3, 4, 5. Right? So you deprotonate the alkyne first, and then you add in the electrophile. Right? You turn the alkyne into a nucleophile, then that can attack, kick out the bromine. Gets you here.
The pi bond isn't it?
Nope. Remember, because alkynes, right? Terminal alkynes, the CH sets here.
The bond angle?
Well, the sp orbital, right? Putting the negative charge in that sp orbital, that makes that acidic. Remember that? I was like, well, first we learned to make carbon-carbon bonds with alkynes. Yep. And then, now if we want to go forward here, what do we use, Joe? H2 and?
Lindlars.
And Lindlar's catalyst, not, Linds. Right, we don't want to use H2 palladium on carbon, that would take us all the way down to the alkane. If I wanted to use the anti-Markovnikov product here, what else would I use? From the alkene, I want to add the OH on the less substituted carbon. We use, what do we use? Less substituted carbon, anti-Markovnikov product?
BH3.
BH3. Yep, step 2 is that H2O2, OH minus, very good. And then if we want to turn a primary alcohol into a carboxylic acid, we want to use what?
The chromium.
Some sort of chromium. Right. There you have it. So another alternative pathway that's on sapling, they actually go from here, and you could actually do BH3, step 1, step 2, the H2O2, OH minus, and that takes a terminal alkyne, right, and turns it into first, I'm going to use black, first an enol, right, where this would be 2, 1, 3, 4, 5, but then enols tautomerize, into aldehydes, 2, 1, 3, 4, 5. And then aldehydes in chromium, right? Aldehydes still have 1 alpha CH left, and they can get oxidized in chromium all the way to the carboxylic acid. So even from this way with chromium, you can get all the way to the carboxylic acid. So it actually saves you a step, but it worked too. We have another epoxide problem, which itself is actually a little funky. And they're saying step 1, you have ethoxide.
Which number is this?
This is 23, but this could be any. I mean, doesn't mean it's your 23. Step 2 was H plus. They're saying they're doing this all in ethanol. So be careful when you see a step 1 and step 2. What that means is these two guys don't react with each other. A lot of times what people want to do is they want to have the thing from one, the reagent from one, react with the reagent, the other reagent too. Have this react with the starting material. Right? Add in some H's. So the one tricky part of this is right off the bat, this starting material is actually meso. So it has an internal mirrored plane. Remember what meso meant? Meso means you have asymmetric centers, but you have an internal mirrored plane, and therefore, because of that, you don't rotate plane polarized light. So we are meso compounds, right? We have hands that are R and S. But you cut us down the middle, right? We have an internal mirror plane, right? So we're a meso compound. We have asymmetric centers, but we ourselves are not chiral. So this molecule is meso, so it's an achiral compound. And that makes a difference for one part of the question they're going to ask us. But, so right now, if I just looked at carbon 1 and carbon 2, are they any different on the epoxide? No, they're the same. So, right, and they're both substituted the same, so it doesn't matter. But in this case, are we in basic or acidic conditions in this case to start off? Basic, right? Number 1 has a negative charge. We're in basic conditions. So if it was differences, we'd go for the less substituted one, right? But it's not, so it doesn't matter. So I'm just going to attack. It doesn't matter which one you attack. I'm going to attack that one. It's going to go up. And the key here is if you attacked carbon 2 or 1, you're going to get both enantiomers. And so if you get both enantiomers, what kind of products did you make? If I can equally get both products, I made a racemic mixture. Right, so that's one of the questions. You made a racemic mixture here. All right, so what did we make? In this case, I attacked 2. So that means the H is now up, right? Because when we do an SN2, attacking epoxide, it's like an SN2. So you do the inversion of stereochemistry. Don't lose these carbons. Right? These carbons are still there. They still matter. Saw a lot of carbons being lost. O minus. And then, of course, we could have the other product where this attacks carbon 2. And that would, of course, be the enantiomer of this. Right? So we have an equal opportunity, right? There's no preference for 1 or 2, right? Both the same. So if there's no preference, right, we'd get either 1, and so actually get a racemic mixture. But I'm just showing 1. So then once we're done using the first reagent, the second reagent is H+. So what do you think that's for? If I added H+ in here, why do I need to add H+? To protonate the oxygen, right? If I'm doing this in a sep funnel, what is this soluble in water or an organic solvent? Right now it's soluble in what? Water. So I need to protonate it so it goes in the organic layer. Then I can rhodevapid it and isolate it. So the final product is that. OH. Plus it's an enantiomer, which of course looks like this, which I can draw. There's either an enantiomer. If this is carbon 1, this is carbon 2, 2, and 1. So you get a racemic mixture in both enantiomers, and you got to. They also want you to ask what are the stereocenters? Are they RS, SR, RR, SS, things like that. All right. We have a secondary bromide. We're trying to turn it into a primary bromide. So 1, 2, 3, 1, 2, 3. So again, we're looking at, do we add any carbons? No. But we took what was the functor was on carbon 2, and now it appears to be on carbon 3. So it went from a secondary carbon to a primary carbon. So that should make us think of anti-Markovnikov at some point, right? We had to do something. And what ways do we know how to do anti-Markovnikov? There's only actually, we only know one way, and that's with what? The BH3 and the water, right? And that makes us an alcohol. Do you guys know a way to turn an alcohol into a bromine? Activated, right? All the activation alcohol ways, right? So we can make the bromine from the corresponding alcohol, right? 1, 2, 3. And we could say, well, where can we make alcohols from? What is the starting material? From an alkene, that's right. And to make an alkene, we need how many leaving groups? Just the one, right? So going forward, what kind of reaction is this going to be going forward? An elimination? What kind of elimination? We only have one choice. What kind of alkyl halide is this? Can you make carbocations from secondary alkyl halides? So it's going to be an elimination, so it has to be which type of elimination? E2. Right? E1 goes to a carbocation, E2 no carbocation. So that means we need a base. What kind of base should we use? Big, bulky with a negative charge. You betcha. Right? Because we don't want it to do SN2, so we want to make it large. Make it reactive and large. So it just does an E2 reaction. Now, if I want to make the anti-Markovnikov alcohol, what would I do? The BH3 first, and then the H2O2 OH minus. That gets us the anti-Markovnikov alcohol. Now there's a couple ways to do the second part, and they're probably going to let you do all those ways. But if you want to add a bromine, you could use HBr, would work, right? You'd activate this and do an SN2, right? Because you can't form a primary carbocation. What else could you use to add a bromine? I think of two more ways you could do it to add a bromine. You could go through the tosyl, right? Make the O tosyl, and then add in NaBr, like Na plus Br minus, and do that. Or what's the way they want you to do it? The PBr3, right? Usually that's in pyridine as well. PBr3. That's the way they want you to do it. This is number 28. We have this alcohol, and we want to turn it into this alcohol. So let's try to number our carbons. Number our carbons: 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So what happened here? Do we add any carbons? Didn't add any carbons. We started out with a tertiary alkyl leaving group, and we end up with the OH on the primary carbon. So again, we should be thinking some sort of anti-Markovnikov thing is probably going to happen here. And how many ways do we know how to do anti-Markovnikov? Just that one, so that's pretty easy. Next week I'll teach you another one, but one more to the mix. That's with the bromine. That's going to be really tough. It's not, right? So we only know one way, so we should always be thinking, well, there's going to be a BH3 somewhere along the way here. So if I would take one step back, where did this alcohol come from? What was the starting material? What did it look like? What was the starting material?
It's an alkene.
Alkene, where was the pi bond at?
Between 3 and 6.
Between 3 and 6, right? Had to be between 3 and 6. 1, 2, 3, 4, 5, 6. Right? And now, how can we make this alkene? It's an alkene, so we need to have. We made one pi bond. How do we add one pi bond?
You can
an E reaction of some sort. But can we turn an alcohol into a good leaving group and do an elimination reaction?
I think so.
Yeah, I think so too. So maybe we can go back to here. Now from here, there's multiple ways you could do this, right? But if you want to get this alkene, something special about this alkene, would you consider this the Markovnikov alkene or nope, wrong Russian? Is this the Zaitsev or non-Zaitsev alkene, do you think? Coming from this, right? If you're looking at carbon, if this is your leaving group, which ones are the beta carbons? Where are the beta carbons? If this is our leaving group. 6, 2, and 4. How many types of beta carbons do we have? 2. And probably, if we're going to take a beta H, which carbon are we going to take it from? Normally, we would take it from what? 2 and 4. Why? Because that would give us the more substituted alkene, the Zaitsev. But look at here, we're not getting that. Oh. So we probably can't do the H2SO4 because H2SO4 would activate this, and then we do an elimination and get the Markov, or wrong Russian, the Zaitsev alkene. So how are we going to get the non-Zaitsev alkene here? And how are we going to do it? So there is a way to do it. We have to activate this alcohol, and then what do you think we're going to have to add in? So this is already a tertiary alkyl leaving group, right? So what way do you guys know how to do an activation and make that product and have it stay?
We don't.
Yeah, you do. It's one of the ways to activate an alcohol. So we know it can't be HCl, HI, HBr, because those all do those SN2s. Zinc Cl2 does an SN2. PBr3 does an SN2. PCl3 does an SN2. SOCl2 does an SN2. Which is the only activation method that doesn't have an SN2 built into it? The only one left?
Could be
Nope. That's like H2SO4. Which one? How can we activate the alcohol and not have an SN2 happen at the same time? Which is the one way we can activate the alcohols and not have an SN2 happen all at the same time? The tosyl chloride. Right? The tosyl chloride. And none of those other methods will work, right? Because all those involve an SN2. And this is a tertiary alkyl leaving group. Does SN2 ever happen with tertiary things? So the only thing that works here, the only way this is going to work, is if we use that tosyl chloride. Right? So that first, after we do that tosyl chloride, probably in pyridine, this is step 1, that's going to give us what? That'll give us this OTS. And we can just make that, and that'll sit there, right? So that's like a tertiary alkyl leaving group, right? That's like a tertiary alkyl iodide. Remember the ways to get the non-Zaitsev products? We either had to use fluorine as a leaving group. That doesn't appear to be an option here. We had conjugation. And what was the last way to get the non-Zaitsev, guys? Hang with me. Last way to get the non-Zaitsev was what? We have a tertiary alkyl leaving group, and what kind of base do we have to use then? So I already have a bulky alkyl leaving group. What kind of base do I need to use? To get elimination, just the opposite. Big. Because that way, if I use the big one, then I can't get to 2 or 4. I can only go for 6. And that's why I get the non-Zaitsev product. Remember the 3 non-Zaitsev ways. Conjugation, fluorine as a leaving group, or a bulky alkyl leaving group and a bulky base at the same time will get you the non-Zaitsev one. A little tricky here. Right? So don't forget those 3 non-Zaitsev ways. They still matter. But tosyl chloride is the key. Right? Tosyl chloride is the only activation method that works really well with tertiary alkyl leaving groups. Yes?
So besides like straight memorizing, like, oh, tosyl chloride works well with the tertiary, like, could you say that tosyl chloride is the only one that kind of holds on to the OH group and like doesn't automatically just rip everything off? Or is that kind of wrong?
Yes, no, the tosyl is the only one that holds on to the OH, and there's no extra. The other ones, the other activation methods, they create the leaving group and it leaves all in that same step. The tosyl, you activate it and then you stop, so it doesn't leave right away.
Oh, okay.
Yes, but tosyl is the only one that really works well for eliminations.
Oh.
because those other ones, because they have that SN2 that happens in their activation. On a tertiary, that will never happen, so they don't work with tertiary alcohol. So tosyl does. Good question though. Yeah, tosyl is the one that kind of holds. It stops. It doesn't keep going, right? Lets it make the alcohol activated, and then nothing else attacks it until you want it to. All right, so looking at one that kind of highlights how the tosyl chloride activation is different than the other activation methods. So D for deuterium, so it's hydrogen with an extra neutron, so it's different. And this is just CH3 up here. So one way we could go would be with SOCl2. So that mechanism we should know. This is in pyridine. But within that mechanism, within that activation, we actually do an SN2 reaction. Right? We activate the alcohol at the same time chlorine comes back around, right, intact. So we end up with, if this is, let's see what Stereocenter this, what configuration is this? RS. So 1, 2, 3, 4. 1, 2, 3, that would be what? S. That means the first product of an SO at the activation should be what? R. What's the product of this activation? What do I actually make? Does the chlorine end up on the molecule? Yes, it does. With SOCl2, it does. Right? And it also inverts the stereochemistry. So the way to draw that, you don't need to change the wedges and hatches. But what you do need to do is put the chlorine on the other side, right? If this was leaving, the chlorine came from the back side, so now the chlorine's over here. And we want to double check ourselves, right? If we were S, we wanted to end up being what? We better be R. So 1, 2, 3. 1, 2, 3, that is indeed R. Excellent. Right, but this comes back to that zinc Cl2, PBr3, PCl3, SOCl2 has a inversion, an SN2 step in the activation always. The tosyl chloride does not. Right? So if I was doing this with tosyl chloride, so TsCl in pyridine, the product of that would be this. Notice, is there any inversion? No, all we've done is activate the alcohol. The tosyl group is held on, right? We just activated the alcohol. So do we change the stereochemistry at all here? No, so this one is still S. And when they're trying to show you in one of these problems, I think I had this in the homework too, or in the class notes. Yep, I did. So now if I add in a nucleophile here, if I add in S minus, what am I going to do to the stereochemistry? I should invert it, right? D, H, CH3, and now there's the S and the methyl off it, and this should be R. That's with tosyl. So in the end of the day with tosyl, right, when I put the tosyl on and actually activate the alcohol, did I change the stereochemistry at all? No. But when I use SOCl2 and activate the alcohol, did I change the stereochemistry? Yes. So now for this one, if I add in that nucleophile, what's going to happen to the stereochemistry here? It's also going to invert, but it was already inverted once. So when I have that sulfur attack, I've essentially done a double inversion. Now this is back to S. So here I activate with SOCl2. Part of that mechanism is the chlorine coming back around and attacking and doing an inversion. So I went from S to R. But then if I added another nucleophile, right, I kick out the chlorine, I'd go back to S. With tosyl, you can activate the alcohol, it stops. There's no SN2, right? The tosyl just stops. Right? It's the one that doesn't have the SN2 in its activation mechanism. We could isolate this and then add in whatever nucleophile we want, then do the SN2. So we went from S to R then. That makes sense? So let's do a problem where we have to figure out how to form an ether. All right. So in this case, we've added a carbon-carbon bond. All right. Specifically, we've added this bond right here. All right. So if we were to break that bond, there'd be an oxygen on one end and let's say carbon 1 on the other end. So every bond we form comes from an electrophile and nucleophile. So the oxygen and the carbon, which one do you want to be the nucleophile? The oxygen or the carbon? Who's going to be the nuke? Oxygen, that makes sense. So I'm just going to call it O minus then. And we want to make the carbon 1 delta plus. How would I make that carbon delta plus? What should I put on it? An I. Sure. Good old iodomethane. Right, now be careful when I draw it like this. That is a carbon there. Even though I draw the hydrogen, that line is not just a mistake. That is real. Right? That's a carbon. Okay? Well, how could I get here? How could I make... Right, I can add in iodomethane. That makes sense. I can add a methyl iodide. How would I turn this alcohol into O minus? What would I need to add? A base. So I think one of the options they give you is NaH, sodium hydride, H minus, because then the product is a gas, H2. Right? If this guy attacks, that gets us here, and then we do a SN2 reaction. We attack the carbon, iodine leaves, and we get our ether. And that gets us to the product. So it's just SN2. All right, number 25. This is a fun one because, well, they're all fun. This is particularly fun. MCPBA, that's O1. A 2 is H plus. So which one of these alkenes do you think is most reactive? They're all conjugated. The one that's not? Why? What? Yeah. And so why is that one more reactive? Because it's not in the aromatic ring, right? Right. We don't want to break up aromaticity, so we'll attack this pi bond. These guys are all fine. They do their own ring. They're in the aromatic ring. Let them do their own thing, right? See you later. Right. So let's attack that one. So that's where we'll put the epoxide. Oh, there's water in there too. Good. Oh, ooh, this is a really good one. I'm getting pumped.
You're welcome. You're that kid that got excited on exams. You were like, yes.
Okay, so we made this epoxide. That was step 1. Now it's step 2. Right? We have H plus and water. And of course, this is going to give us acidic conditions. So we'll protonate. And now the question is going to be, which carbon are we going to attack? Dun, dun, dun. I'll number them for you so you can decide. 1 and 2. Which carbon do you think is going to be the most delta plus? Can handle the plus charge the best? Which one can handle the plus charge the best? Why?
Because it's closer to the aromatic ring.
By God, yes. I would even say that's in the benzylic position. So yes, carbon 1 can handle the plus charge the best. That's where water will attack. We're in acidic conditions. We want the more substituted or the more stable, right? Because this one, they're both secondaries, but carbon 1 is benzylic, right? So that's even better, right? So that's where it attacks. H plus is a catalyst. I'm going to skip a step. But actually, no, I'm not going to write it. You guys can figure it out from here.
Wait, what?